everybody. So yeah, my name is Alba Malaga, but I'm no longer working at Brown. I'm working now in France, more precisely in Saint-Dié-des-Vosges, and I will be talking to you about this little precious polyhedral flat tori, which with my collaborators Pierre Arnoux and Samuel Lillier, we are actually able to make from paper since. At first, I would like to fix the vocabulary. 3 keywords. Torus, flat, polyhedral. Okay, so what is a torus? Is just the surface of a live buoy, a surface of an inner tube, a surface of a donut. What do all these shapes have in common? Well, they are kind of deformations of this prototype round torus, and in general we will say that any topological space, any shape that is kind of a continuous deformation of this is a torus, and this prototype round torus is obtained by sliding a circle around a larger circle. So that means in particular that the product of two circles is a torus, but the product of two circles from a mathematical point of view is actually the same thing as a square with opposite sides identified. So when you make an actual square of paper, you cannot do the operation that I just showed on the screen, but you can imagine doing it by bending it. That's what we mean by continuous deformation. But on the other side, you can also make it abstractly and say, well, I'm identifying the opposite sides of my square and keeping the same geometry inside. So then with these geometric lenses, we will say that a square flat torus is the one obtained by identifying the opposite sides of a square. And in general, a flat torus is any torus that has a geometry that makes it everywhere flat, or in an equivalent form, any topological space obtained by identifying opposite sides of a parallelogram. So for example, this torus here is not flat, the one that you make with donuts. And here I have a first example of polyhedral torus. And this torus is not flat. Why? Well, you can see easily that inside each face you have flat geometry, but on the corners, on some corners you will have too much angle, more than 360 degrees, and on some corners you have not enough angle, less than 360 degrees. This other example also is not a flat torus, and unfortunately, if we want a smooth realization of the torus, it's not possible to do so in the Euclidean space, but if we relax the smoothness requirement, it's absolutely possible. Here is an example that at some point was very, very famous among people loving mathematics, the C1 example by the Hevea team, a kind of infinite smooth fractal, which is super beautiful, but kind of frustrating when you want to trace lines on it because of its fractal nature. So there is the other possible answer is to answer with polyhedral flat tori which are at the same time polyhedra and that have a total angle of 360 around any single vertex. So there is one example of such a polyhedral flat torus made by Taleri following a general method by Virago and Zalgaler. Here is another example taken from a paper by Zalgaler. Here is another example from the PhD thesis of Quintanar. And here is the one that I was showing you at the beginning. With my colleagues, Pierre and Samuel, we have studied this family of polyhedral flat tori with 2 n vertices, with n being at least 5, so at least 10 vertices. This family has been also independently studied by Tsuboi. So to understand how these diplotori, how these tori are made, think about a hyperboloid. When you have 2 hyperboloids with the same 2 supporting circles, you take the union, you get a torus. But now the hyperboloid is roulette, but instead of taking a roulette surface, you can discretize it and get this kind of piecewise linear rouloids or ploids that we call them, and when you put them together, you get a torus. And because of how was it made, the total angle will be 360 around each angle. Okay, but in practice, how to build such a torus? It is a polyhedron. It is flat, so you can just cut paper, fold it, and glue it, and have a torus. Or you can use one of our glueless layouts, soon to appear at kits.mat.cnrs.fr and imaginary.org, 2 sharing websites for mathematics popularization. And a natural question behind it is, because there is such a large variety of flat tori, can all of them be obtained with this double ploid construction? Can all of them be obtained as diplotori? And well, the tori, the flat tori, they live naturally in this space, which is called the modular curve of flat tori. And like, for example, this point here, the red part represents the modular curve of flat tori, and this point here represents the one obtained from a parallelogram with equal sides and 60 and 120 degrees. And the answer is yes. So the proof has been made independently by ourselves and by Tsuboi. And I have my last 20 seconds, I would like to know if anybody in the room knows who actually invented this concept, because we studied it but didn't invent it. We learned it from Henry Segerman, who learned it from Herrell, who learned it from Rollet, who learned it from somebody who he doesn't remember. The interest in these objects likely goes back to the 1960s, but we don't know who the original author is. Thank you very much for your attention. I hope I didn't speak too fast. Bye.